Our next speaker will be from Bell et al. To make us recommendations for real-time coordination for Artemis lunar surface geophysical science investigations. While we're starting up, keep those questions coming for me in the chat box. Thank you. Whenever you're ready, take it away.
Good afternoon, everyone. I am Ernie Bell. I'm currently finishing up my PhD in geophysics at the University of Maryland. Previously, though, I was an EVA flight controller at JFC. I worked with both Alex and Jackie, who you've heard from earlier today. For this presentation, I'd like to cover a few items with respect to coordinating real-time lunar surface field geophysics. So basically, cover a few areas: what and why geophysics, look at generic strategies that are used in the field for data collection, have thoughts on real-time roles for mission execution, and then go over a couple areas of key importance for optimizing the scientific return of geophysical and geologic studies during the Artemis missions. So next slide. So first off, what is geophysical data and why do we need to conduct geophysical investigations on the moon? Well, geophysical data includes identification of stratigraphic layers of the subsurface, determining various physical, mechanical, and electromagnetic properties, and also looking at heat flow characteristics. Geophysical data can also help to identify and characterize natural resources such as volatiles and looking at mechanical or structural type resources. So how does this fit in with the objectives of the Artemis program? By acquiring these types of data sets, which I've just mentioned and others, we can help to understand the planetary processes of volcanism, tectonics, regolith creation, as well as overall planetary formation. We can help to characterize and determine the origin of polar volatiles, understand the impact history of the Earth-Moon system. In addition, this data can be used to investigate and mitigate various exploration risks, such as potentially through a geophysical monitoring network. Next slide, please. Next slide. Thank you. So now I just want to provide a few examples of the types of geophysical studies that we perform on Earth. They include things such as in the upper left, magnetometry. In the upper right, I have examples of both active and passive variations of seismic studies. Lower left, you'll see some 3D laser or LiDAR mapping of geologic features. And then there's also gravimetry, and in the lower right, some examples of radar sounding that we performed in the field. And there's a number of other studies which I've not shown examples of here. Next slide. So many of these same types of instruments were included in the field work performed by the crews of the Apollo program. Many have already been mentioned today. However, the results only scratch the surface of answering many of the geophysical questions in areas that I've mentioned today. So examples that I show here include portable magnetometer, which was used on Apollo 16. You see that in the upper left. A gravity reading being taken during Apollo 17 in the lower right. We have examples of active and passive seismic equipment from Apollo 16 in the upper right. And then a heat probe that was deployed during Apollo 17, as well as the Apollo 12 LSEP package, which contained a variety of geophysical experiments. Next slide. So what are some generic field strategies that we can apply to conducting geophysical field studies? Two basic types of strategies which were used during Apollo and that we use in the field here on Earth are first a deployable type of single site long-term setup, so both a permanent or a semi-permanent type of setup of a instrument. Some examples of this, or an example of this from Apollo would be actually the passive seismic array, which was deployed over multiple missions. A second strategy is to conduct multiple equipment deployments or take multiple readings along a single traverse route. Things such as the portable magnetometer, deployable explosive packages that were deployed along the traverse route of Apollo 17, and other types of readings that could be used or equipment that could be deployed. So then additionally, there are three basic types of deployments that modes or models that these could fall into. So first, you could have a single site reading or a deployment of just a single location. This could actually be extended then to perform multiple readings or instruments deployments along a single transect. And then third, you could simply extend a transect style model to perform an area coverage using any of a variety of types of grid patterns, either rectangular, spiral, or any others that you might want to come up with or develop. So next slide. So now I'd like to briefly cover some options for general roles for the crew and for MCC science team for missions, for the Artemis missions. For the crew, task types could be broken down into some of the following types of functions or categories. You could have crew-conducted tasks where they were primed for executing the task, which may or may not include a need for coordinating with MCC science. Secondly, you could have a category where the crew is only required to provide oversight, such as maybe a semi-autonomous or an MCC-controlled type of activity that only requires minimal participation from the crew. A third category could be a crew-deployed type of task, where after initial hardware deployment and setup, MCC is now able to fully operate and control the hardware. And then a final category would be tasks where the crew is only required for troubleshooting or recovery from failures of the hardware. For real-time MCC science roles, these could include performing assisted task execution, where the MCC science team provides evaluation and direction and coordination with the crew's assessments. The second role or function would be the MCC science team providing a verification of instrumentation performance, so as expected. And then the third would be for the MCC to verify appropriate data collection and quality of the data. So not only is the instrument working, but we're actually getting the data we were hoping to get. Next slide, please. So what are some specific roles for the MCC science, and what are the benefits of providing these real time? Well, first of all, you could obtain a coordinated instrument placement using a crew's on-site assessment, combining that with the MCC science expertise that they have with terrestrial field work. This is really in relationship to any of the deployment models that I just talked about, such as maybe installation of a geophysical monitoring station or final determination of a grid or pattern or a coverage area for an area survey. Secondly, MCC science could provide real-time evaluation of the data quality and content within the geologic context. So this could inform the timeline activities both tactically and strategically. So MCC science could verify that you have sufficient data collection from the crew, and then the crew can then continue on with their traverse or completion of data sampling. So they may actually have enough prior to what they may have thought. We may get it early and be able to send the crew on their way, basically optimizing their activity. And then finally, MCC science could provide expertise in assessing and troubleshooting instrument operations. So this would include providing both task options based on unexpected features of a location. So if we want to make adjustments real time based on crew assessment, we could help with those results. Next slide, please. So now I'd like to reinforce a couple of items of importance that have already been covered today by other talks, but just wanted to mention them. First one is training. So this is especially important to train the whole team, as has been discussed. This includes engineering, scientists, the flight controllers, the crew, and management, and training them in the various geophysical tasks that are going to be performed. Two primary categories of these types of training could be field and analog training and simulation training. So field analog type training would put the team in a similar environment of which a task will be performed and allow them to understand the objectives, the hardware, refine the steps, improve the overall coordination. And then with simulation, helps improve team communication, understanding the hardware limitations, realizing the impacts of consumables from the mission, and then implement contingency type procedures. Next slide, please. Next slide. And then the second item I wanted to reinforce was the importance of communications to executing the operations, as communications can either be limited by or they can drive the hardware design. So this applies to voice, telemetry, and commanding. For voice, we'd want to look at what the flow is within the science back room and then forward to the MCC front room. And what positions do you have in the back room, and what positions might we need to add in the front room? Also, who does the crew talk directly with? Is it task dependent? Is it a Capcom? Is it a science communicator? What type of position is it? And how many independent are required to the crew? So we might need to also consider multiple independent voice loops from the crew to MCC, as I just mentioned, and also within the crew itself, IVA to EVA type crew. And for telemetry, we want to have the ability to receive sufficient and timely instrument and telemetry. And then finally, for command capability, we want to be able to command instruments in a timely fashion to optimize the use of crew time. Next slide. So in conclusion, real-time geophysical science support will be able to optimize crew execution of lunar surface geophysical science tasks. This will require proper training and planning with the implementation of proper voice, telemetry, and command communications. And we need to draw on past spaceflight experience with an evolution to include modern field capabilities and practices. Thank you.
Thank you, Ernie.